recur to this. Thank you very much. Yeah.
Okay, it's working now.
Yeah, we should. So we consider Brownian motion. We defined already natural filtration, which is generated by all values of our Brownian motion up to some fixed time t. One can think about information that is contained in our Brownian motion. In this, we can access by observing our Brownian motion until time t. We discussed two possibilities of augmenting this filtration, making them slightly bigger. The first possibility is to consider so-called right continuous versions by doing this operation. And the second possibility is to introduce so-called completed version of this filtration by considering these completions of original sigma algebras, where these are null sets, so-called, and they are such subsets of the original probability space that exists measurable sets containing this set and such that the measure of this external set is zero. One can think about the difference between Borel measurable or Lebesgue measurable sets on the real line. You can define measure on Borel measurable sets, and you can spread it, push it onto Lebesgue measurable set by using this operation. And the last proposition we proved, and I want to revisit it because we have also new participants, and we will use this very scheme of proof one more time, at least today, and the whole proof of this proposition is very standard. So it's very important for us to understand how it works. That one moment. Okay, can you hear me?
Yep.
Good, thanks. And both versions of this filtration, and even if you do this, so first, say, add null sets, then take right continuous versions, are such, all these filtration are such that for any s greater than 0, such processes which are shifted Brownian motions is indeed a Brownian motion in standard sense, and it's independent of these filtrations. One can think this as some extension of an ordinary Markov property. Now, I will only consider the case of the last filtration, because the rest is pretty similar. So what I want to do is to repeat the proof to discuss it one more time. So consider function from for fixed s from here, w, and consider any bounded function on Rd. Now, if we consider this device steady, maybe we will even right. Yeah, let's consider just this filtration. We did an extended version less times. Take the set from this device, this equals. Now, because A belongs to this augmented version, there exists belonging to the original filtration such that we can effectively get rid of this difference and switch to the good set. Now, because trajectories of inner process is continuous and f is a continuous function, we can write this as a limit when, say, epsilon goes to 0, symmetrical expectation, FBWS T1 plus epsilon. So we move a bit. Now we can take internal conditional expectation with respect to the original natural filtration at time s plus epsilon. Now, this is measurable, and this, by ordinary Markov property, is an independent Brownian motion with respect to this filtration. So this can be decomposed. But I already have passed to the limit. And this is obviously PA. Control D. No. Control D should work. Now, step 2. If we have step 1, then that means for any delta which is closed, and delta is closed, there is this sequence of functions such that they are continuous, bounded on Rd at Fn converge to delta pointwise. We effectively provide a description of this function last time, but this is like a rescaling of the distance to this set, which is closed. Now that means that for any delta closed, we can use step 1 to conclude that for any A belonging to this WS, P of A according is alive belonging to delta. Why? Because we can approximate this indicator by those continuous bounded functions from the first step and then pass to the limit. So we conclude that this holds. So what this does mean? So effectively, this means that f augmented filtration is independent with respect to the filtration generated by this for any T1, TD real numbers. Why? Because we know the following statement, that if we have two sigma algebras and the second sigma algebra is generated by the set Z function as B is a P system. What is a P system? It is a system of sets that is closed under finite intersections. And the set of closed set is exactly a P system. Then, if for any A from the original sigma algebra and for any B from this smaller set, we have effectively independence, this means that A and B are independent. So in our case, F WS and B is the sigma algebra generated by values of our process. So we have this independence of the smaller sigma algebras. Now step 4, which is the end, is the proof is, we need to recall what this is. And this is one way to describe it by definition is to said that this is the sigma algebra generated by all finite combinations of values of this process. So one can write this as follows. T1, Td plus effectively. But now we can use this result from step 3 one more time. Because this set, this is called generator of a sigma algebra, is again a P system. It's not hard to check, take this like exercise, but it's very clear. It's intuitively clear that intersections of such sets as this are again of this form. So using this again, we can now conclude that the whole original sigma algebra is independent of sorry, sigma algebra ST T greater 0. The sigma algebra generated by our shifted process. Here is shifted process. Here should be shifted process. And this is exactly the statement of our proposition. Now we recall that a stopping time tau is a non-negative random variable such that for all t, for some filtration, so stopping time is defined with respect to some filtration. We considered examples of stopping times and why it's important and why we need those augmentations of the original filtration, why it's important to have them. And one reason is exactly that one need to discuss good properties of stopping times. Now let's define the following sigma algebra. So assume that tau is a stopping time with respect to some filtration, gt. This may not be a natural filtration, doesn't matter. Then we can define this sigma algebra. G plus tau. I putting plus here to indicate that this is not necessarily this right continuous augmentation. This is defined as those sets that for any t, this good property holds. I'm not going to prove this, but I will make the remark that effectively this is sigma algebra exactly generated by stopped process. In the case when gt is equal to the natural filtration. So this all information that available to us if we consider the process up and including the time that it, say, hits some good closed set. Now we are ready to formulate two main results. The first result is going to be the strong Markov property in a most general, maybe not most general, but a general form. And the second result will show us which filtration should we take to define stochastic integrals. So this is a version of strong Markov property, effectively. Markov property. So assume we have filtration gt for any positive, non-negative s. This ws, which recalls it takes time t and send it to a shifted value of a Brownian motion, is independent of gs Brownian motion. So any filtration from the previous step works. Then the process that takes and shifts Brownian motion by a finite tau is a almost surely finite stopping time with respect to this filtration. Is again a Brownian motion. Independent of this g plus tau we just defined. So before proving this, let's look at some corollaries. So effectively, what we will need a bit later in this course is that this the sigma alpha generated by the value of the process at time tau and what happens after are independent, and for all, say, bounded f and positive or non-negative times, we can calculate mathematical expectation of the finite with respect to the finite dimensional distribution of the shifted Brownian motion conditionally on this sigma algebra by using the following. expression. Where W tilde X is a new Brownian motion started at X. So we effectively just take a non-random starting point, calculate this expression, and then substitute inside of this expression this random variable. And we obtain a random variable as the answer. This very often written just in this form. So we calculate the expectation for a Brownian motion that start at some fixed point and substitute here a good random variable. This needs to be proved, but I think it's pretty clear that this should work, and we are all aware of how it works. So let's just prove this strong Markov property. We will do this again by steps. So at the first step, we will introduce such specific approximation from above of our stopping time. When m to n, m plus n, 2 to the power n, and I think this direction. Here should be n. Now tau n almost surely converge to tau. This is easy to see because tau n minus tau always satisfy this relation. And we need two properties of this tau n. Tau n, I gain stopping times. Since we have a fixed filtration, I will not say stopping times with respect to this filtration, just say stopping times. And for any A belonging to this newly introduced sigma algebra, this set is measurable with respect to a smaller filtration. Now let's prove both statements. So first, we need to check by the definition what stopping time is, that this works. So this tau and tau n intersections that m plus 1 divided by 2 to the power n is less than t. This so there should exist some m of t such that mt to n, this half-closed interval contains our t, right? So this means we take union for all m starting from 0 to mt minus 1. Why minus 1? Because tau equals to the right side of this interval. So it's slightly bigger than we need. And this is exactly the tau is less than mt to n, which belongs to gmt to n. Mt is less than ft, so this belongs to gt, which is exactly the definition of stopping time. Now, to prove the second property, proceed as follows. Tau n equals m divided by 2 to the power a. This means it is less than this, but greater than this by the definition what tau n is. And now we do something very similar to what we did when we were proving just some properties of stopping times. Now, this part equals this part equals to this part, equals this part. Now, again, this can be written as intersection over all j, natural that tau is less than m minus 1 to the power to n minus 1 over j. And then we take the complement of the set. And obviously, this belongs to gm to n, this belongs to even smaller. So the whole expression belongs to gm divided by n. I'm checking whether recording is going. It should work. So now we can proceed to the second step. Now consider g plus tau. This is the set from the sigma algebra we are primarily interested. And now consider t, say, m, and numbers, let's say n, but n, real numbers, and let's consider such expression. Indicator of a and this is almost a characteristic function of finite dimensional motion inside of the shifted Brownian flow Wt tau. Again, in the previous proof, we considered just bounded continuous function to prove independence of two sigma algebras to approximate some good sets that will generate that sigma algebra. But if you can consider bounded continuous function, we can consider functions of this form. Because if you have bounded continuous function, we can consider bounded continuous function on a limited interval. If we can do this, we can use different types of bases, and this is well-known basis from the theory of Fourier series. Again, the same trick. We can now, using the fact, or maybe D is bad, because let's keep notation consistent. I will switch here to n and here to D and here to n. Alpha k, and here I will just write tau n plus t k plus 1 minus. This is true because the Lebesgue eliminated convergence theorem. And now I can introduce inside one additional conditional expectation. So nothing changes here. I will just write it in this way. And here I want to introduce conditional expectation with respect to the following: d minus 1 plus, before doing this, I think I need to do the following. Let's use the definition of tau n. So this is indicator that tau belongs m divided by this, m divided by this. Sum from 1 to d minus 1. Here stands alpha k, v m plus 1 divided plus tk plus 1 minus w m plus 1 and plus tk. So I just substituted the value of tau n inside of this expression. Now, because this is integral over omega, and this is exactly the sum of indicators, and the product of any pair of these indicators is exactly 0, we don't even need some, say, Fubini theorem to take this outside. This just integral is the sum of integrals because they integrated. The integral is considered over the set of non-intersecting sets. Now I can do what I wanted. And I will introduce additional conditional expectation inside. This expression, nothing changes here, so I will just leave it as there. And now I can start like clipping this expression one by one, starting from the very last one. Td minus 1 plus m plus 1 times 2. So what we achieved by using this is that we get effectively rid of stopping time in the sense that this is something that appears in ordinary Markov property. Now, here, indicator A, indicator tau belongs to this. We just proved this in the previous step. This belongs to this sigma algebra, which is strictly smaller than this, even. Secondly, for any k this is less than d minus 1, this random variable is independent by the ordinary Markov property. Is measurable with respect. I was thinking, but measurable with respect to this. And the last one is obviously independent by the ordinary Markov property, not strong Markov property, just the ordinary Markov property. That means that we can obtain something like this. Indicator A, indicator tau belongs. We can just take this outside. And we can take outside this expectation for all the sum except for the very last term. So k is now from 1 to d minus 2, alpha k, w, n plus 1, plus 1 divided 2 to the power n plus tk minus this, k minus 1. And here we just have expression alpha d minus 1. Here k plus 1, here k. just effectively and 0 td minus 1. And we can do this one more time again and again to get rid of everything in this expression, just to calculate this mathematical expectation to arrive at the following limit. Mathematical expectation indicator A, indicator tau belongs to times the mathematical expectation, even the product, say, from 1 to d minus 1, now this sum is just 1, so we arrive at p of A times this product. Now, if we take this A to be equal just to the whole set, to the whole omega, we immediately conclude in particular that W tau is indeed this Brownian motion, because finite dimensional distribution are Gaussian with proper zero mean and proper variance. This is effectively says that W tau is Brownian motion. But moreover, it also proves, let's do this as a step, whatever. That this sigma algebra is independent of this. But now we can use exactly the same formulation in the previous theorem. And we can conclude using this P lambda theorem that should be independent of the sigma algebra generated by the whole. And that's effectively it. That's a strong Markov property. Now, the important corollary of this Markov property is that it allows us to say, as I said before, what filtration we need to use to define stochastic integration. And effectively, it claims that if we have a natural filtration, as we just add null sets, it's already right continuous. So in particular, hitting times for open set, first moments when a Brownian motion hits an open set is a stopping time with respect to this filtration. It was something we really wanted from our filtration. And this is what we effectively obtained. We don't need to go through two-step procedure. We obtain everything by taking just one step. And in the previous lecture, who is not familiar with it, we discussed why it's important to include null sets anyway, so we're not losing anything effectively. So let's prove this actually. It's not hard, it's just a bit tricky. So step 1, let's consider Borel sets, a selection of Borel sets, and selection of times less than Sn, less than T for this fixed T, less than R1, Rm. And now I will consider the following conditional probability. Probability is that Wsk belongs to Ak for k from 1 to n, and Rg belongs to Bg for g from 1 to m. conditionally with respect to this right continuous augmentation of already augmented with null sets filtration. And what to say that this is in the end just T tilde. But now we can use strong Markov property because obviously tau is a stopping time. It's a very simple stopping time. It's just a constant stopping time. And that means that this can be taken out. So effectively, this is just a random part. And this is a probability given that we start from WT. So this is the corollary for the strong Markov property. Now, this is obviously is a T-measurable random variable, because this is a function of WT, and it's measurable with respect to this filtration, and this is obviously measurable with respect to this filtration. So step 2, we define, firstly, the set that all sets of cylindrical sets from step 1. So these all sets that can be described in this way. And by D, I will define the set of all sets that even live here, such that the conditional expectation with respect to this augmented right continuous version of the filtration has a version that's measurable with respect to a smaller sigma algebra. Now, by the previous part, we consider that if we consider these good sets, they have this good version. However, because effectively augmentation with null sets doesn't change conditional expectations, it's just adding something that is happens on the event of probability 0, we now can conclude if R is a P system and D is a D system, a lambda system. D system is lambda and lambda system are the same thing. And D is a lambda system. Then D, by the P lambda theorem, which we discussed in the previous lecture, should contain the sigma algebra generated by A. But sigma algebra generated by A effectively coincides like with this because we can add those sets of null sets into this A. Adding this something of measure 0 doesn't change the conclusion of this step. It happens on the 0 set, it doesn't change the conditional expectation. Now, obviously, the system of sets of this form of cylindrical sets is a P system. So effectively what we just need to prove that D is a lambda system. Is a lambda system. So by definition, that means that omega belongs to D. That's obvious. Now, that if 2 belong to D and A1 is greater than 2, that its proper difference is again in D. But this again is true because the conditional probability is a linear operation. So it's just a difference of conditional probabilities, and if both have a good measurable with that sigma algebra we discussed, then the difference also has. So effectively, only the third property needs to be verified carefully. We need to claim that this has a f t measurable version if an satisfies this condition and an are increasing for any n. But because they're increasing, this union, this should be union, is by the dominated convergence theorem for conditional expectation. It's just a limit. But the limit of measurable function is again a limit measurable function. So we have this conclusion. So we can conclude that for any A belonging to which is equal to just A because it's measurable with respect to the sigma algebra, has a version that is measurable with respect to a smallest sigma algebra. So what means a measurable version? That means that there exist random variables that coincide with our random variable with probability 1 that is measurable. So there exists some psi. Psi is measurable, and psi equals our indicator A almost surely. But that means that the difference for our A and this condition is less than when this doesn't happen. But probability, as we said, is 0. So this is a null set. So up to a null set, this is measurable with respect to this. But we can change anything on null sets by the definition of what this augmented filtration is. So this effectively means that indicator A belongs, is measurable. Measurable and A belongs here. Because there is a set that lives here, and the difference of this set and this set is of outer measure 0. But now this holds for any set in the right continuous version of this filtration. So this cannot be larger. But this effectively means right continuity. So adding the second step doesn't really work. So from now we can just take natural filtration of a Brownian motion, add null sets, and be happy. There is an interesting corollary from this, which is typically called Blumenthal's 0-1 law. And it claims that the natural filtration possesses this nice property. These two sigma algebra contain only events of probability 1 or 0. So we know that the conf say iterated logarithm for Brownian motion, and the corresponding relation holds its probability 0 or 1 automatically. And the proof is very simple now. This is less than this because we added something here. This is less than this, but this equals because it's right continuous. But this is exactly the sigma algebra generated by null events. And null events exactly have probability 0, their complements into probability 1, so this holds. In particular, if you return to the previous lecture, we were concerned about what happens if Wiener process hits the boundary of an open set. We said that the problem is the corresponding time it happens for the first time, and why we cannot immediately conclude that this is a good step in time. It's because to know whether it goes inside of this open set or outside of this open set depends on the behavior of the Brownian motion after this time. But now we know that from this Blumenthal's 0-1 law, it either goes here with probability 1 or stays out. So it kind of answers mostly that question. So now we can proceed to, let's say, naive integration. Integration and variation of Brownian motion. So we want to define expressions of this type. If you want to do this just by taking a trajectory of Brownian motion and looking at this as a Riemann-Stieltjes integral, we need some properties of W, which is not effectively going to happen. So to define, say, 1 as a Riemann-Stieltjes integral, we need the W has bounded variation, and we will repeat what bounded variation is in a second. And one can say, if someone is very knowledgeable, to define that we can consider a more general version of the Riemann-Stieltjes integral as so-called Young integrals. Typically, it's formulated that if you want something like this, then you need either the beholder continues with alpha plus beta greater than 1, or alternatively, you need that f has pair variation, g has q variation greater than 1, and 1 over p plus 1 over q is greater than 1. However, as we will see, nothing works for the Brownian motion. And I will make this remark right now that while I'm going to show that you cannot define pathwise integrals with respect to a Brownian motion just by taking the trajectory and using calculus, and you need to go outside of calculus, this partially is not true, because there is such thing as rough path theory that does construct such integrals, but in a very specific way. We are not going to discuss rough path theory in this course at all. So given a partition phi, which has the following form: Tn equal T, or some fixed interval from 0 to T, we can define P variation for a function f as the following sum. F dk to the power of p. Typically, p should be greater than 1, obviously. Now, and we say that f, a non-random function, has finite p variation if supremum over all pi such that the size of this partition goes to 0, and it can be denoted just Vp of y is bounded. So regardless of how small partition is, there is some bound for this expression. So this is the meaning of this two statements. Now, if function is Holder continuous with alpha, it has finite variation of degree 1 over alpha, and if it's continuous, vice versa also works. And because the trajectories of Wiener process is are continuous, we effectively can switch between these two forms of discussing unit integrals. And bounded variation is one variation. However, for a Wiener process, the following proposition only works. So let In be a sequence of partitions of 0t capital such that every partition has this form, and dn, which is the size of the partition, so k from 0 to n capital n plus 1 goes to 0. Then for Brownian motion, we have this convergence in L2 omega, so in square mean. A small remark, we are not going to prove this, but actually convergence also happens almost surely. So two variation of a Brownian motion is continuous in this square mean and also almost surely. Let's prove this. It's not hard. So I will introduce such expressions, and Sn is going to be just the sum over all possible psi and k. Then, to prove this proposition, we need to consider such difference squared. This is by definition of convergence in L2. But this effectively means Sn minus t squared, just because we introduce such notation. Here, and this is important property that we will use later, this is sum over k. I will just write sum over k without writing this expression because I'm not going to do anything with this sum, splitting them, this sum, splitting them, or something like that. This is a mathematical expectation of 0 Tn k plus 1 minus Tn k squared. So it's just a square of a random variable. This is Gaussian random variable. So it's just the sum of k of variances, and this is just t capital. And sorry, here should be t capital, obviously. But now our Sn minus t squared equals Sn squared plus just t squared minus 2 tsn, which is equal mathematical subcase n squared plus t squared minus 2t, and this is again t squared, which leaves us just mathematical expectation Sn squared minus t squared, which can be again rewritten in a nice way. So this is just a variance of this Sn. But because Gaussian process has independent and increments, this is the sum of variances. So this is effectively the sum over all k mathematical expectation of w tn k plus 1 minus w tn k to the power 4 minus mathematical expectation tn k plus 1 minus tn k squared one more time by the definition of variance. And now I give this to you as an exercise. Mathematical expectation for any natural p is actually 2p minus 1 here 2p minus 1, p minus 1, 2p minus 3, so on, times sigma 2p. In particular, the force moment. You can prove this by hand just using integration by parts formula. This is just sum over k, 3 tnk plus 1 minus tnk squared minus tnk plus 1 minus tnk squared. This word. But it's obviously less than 2t dn. And this goes to 0 and n goes to infinity. One prominent corollary is that for any p less than 2, the corresponding variance of Brownian motion is infinite. In particular, it doesn't have one variance, so it cannot be used to define something like Stieltjes integral. It can be used to define Young integrals, etc., because it's not enough. Now, to see why this happens, let's consider. I will use notation from the previous proof. Consider this expressions that we just had. This is less than here 2 minus p, that's why p is less than 1. And here I will just write the sum of t and k to the power p. So just clipped a bit from this expression. Now, if this is not true, then this is less than this maximum tn k plus 1 minus tn k to the power of 2 minus p. The supremum of all partitions. But W has continuous trajectories, in particular those, and thus those trajectories are uniformly continuous. That means that this should go to 0 when it goes to infinity. Which means that if VPW is finite, then sum WT and k plus 1 minus WT and k squared goes to 0. Because it is in the left-hand side. But we know that this goes to T capital in L2, so there is at least a subsequence for which this expression goes to T almost surely. And however, if the P variation is finite, this should go along that subsequence also to 0, which is contradiction. So Wiener process has infinite variations. Another conclusion that we can draw from this is that while pairwise integration doesn't look promising, maybe L2 approach is what we need to take. And this is exactly the route we need to take. So from now on, again, we will consider just natural augmented filtration, which is right continuous and everything is good about it. One can do this in a more slightly general way by considering it so-called admissible filtration. So it's just good complete right continuous filtration with respect to which a strong Markov property holds. But for our purposes, it's more than enough to consider just ordinary filtration. Now we need to define what are the processes that we are going to integrate in terms of measurability. And the process, the stochastic process psi of t, is called progressively measurable. Progressively measurable, or just progressive. With respect to this filtration, I will drop tilde because we have only one filtration. If all mappings that take the pair S omega and calculate the value of our process, consider it where t is less than t capital, endowed with the product sigma algebra, are measurable. So every restrictions to a smaller index set preserve measurability effectively. So that is for any Borel set in RD, the set of all S and omega such that S lives here, and for any t less than t capital, and omega from omega capital, and xi as omega belongs to delta, this belongs to this product sigma algebra. So what is product sigma algebra? Recall this is by definition the sigma algebra generated by all such rectangles. These are Borel set on this smaller interval, and A wait, it should be T here. It should be T here, obviously. It should be T here. Most stuff that you can encounter in real life is progressively measured effectively. So it's not a problem to consider only such processes. So let's consider just one example that we will finish. Let tau be an almost surely finite stopping time. I recall the stopping times were defined in such a way that they can be infinite. But here we just take it positive. And psi is progressive. Then the process so-called stopped process is progressive again. Is progressive. So the proof is again very standard in the sense that we introduce additional mapping. Let's consider additional mapping from 0 t capital times omega that takes the pair of points and sends it to t minimum t omega omega. Then our psi tau can be considered as a composition. So firstly, we calculate instead of t this expression random, and then we put it inside of psi. So now what we need to check that this I is measurable in a proper sense because the composition of measurable sets, measurable matrices against measurable. We need to check, or more precisely, it is sufficient to check that I is measurable from zero t. Now we can note that we already discussed, so that Zhao, we already discussed what it is. We can be a bit more specific that this is also the sigma algebra generated by a smaller set. So we still take all like sets in rectangulars where the right hand side is given in all, with all sets from the original sigma algebra in omega, but we can take smaller sets I think it's s less than t. Why? Because we can consider in these rectangles not Borel sets, but open sets, or any good system that generates the corresponding Borel sigma algebra. Effectively, this is it. And now we can consider 0 t times f. So this is just here s should be obviously, and here should be r. Omega such that tau omega s and omega belongs to f. So we take this set and consider the pre-image of this set. And now again, a very standard in this theory argument that you need to consider two cases. Omega immediately goes here, r stays here, and we consider two cases here, intersections. Tau omega minus r less than s, tau omega less than s, and tau omega minimum r is less than s, but tau omega is greater than s. So we consider two cases, when this tau minimum is equal to r, and when this is given by tau omega. So this r omega goes to f, tau omega less than s. In this case, let's think whether I'm right or not. One moment, please. Okay, maybe we can return to discussion. So if tau omega is less than s, then this minimum is given by tau omega. If we just get rid of this r, it doesn't matter. It's already less than s. Okay. Now, if tau omega is greater than s, then this minimum is given by r, and we have this condition. And that we can rewrite in this case. Like, this is obviously easier. This is just 0s times f union, and we are left with this expression, which is effectively can be written as, I think, something like 0 t times those omegas that this happens, because there is no restriction on r at all. In any case, this is going to be 0t times ft because of properties of stopping times. And a final remark that in literature, you will typically find integrals dws where f is adapted. That means that it's jointly measurable as a function of omega and s, and such that for every t, ft is just ft measurable, not like jointly measurable, not with respect which is more rich sigma algebra, but just as a random variable is measurable. And in fact, one can build the whole theory of stochastic integration for such expression, for such adapted processes. Every adapted process, every progressively measurable process is adapted, but not vice versa. However, adapted processes are not very different in the sense that every adapted process has a progressively measurable modification, and every adapted process that has some kind of continuity, for instance, is adapted at the right continuous, is automatically progressively measurable. However, proving that every adapted process has a progressively measurable modification is not very trivial. And when next time we will be building stochastic integrals, we will need some approximation of progressively measurable process with simpler processes. And this is exactly the place where you need to do some technical work in the case of adapted processes. And that's why, to avoid doing that work, we exclude adapted processes. However, in general, in literature, in papers, we'll see that in this integral, f is just adapted, not progressively measurable necessarily, but it doesn't mean much in practice. Does someone have any questions? Yes.
Don't we need here to make a constriction on 0t, like not ft, but so f constricted to 0t?
No. This is exactly adapted process f is called adapted if two properties. This, just which takes as ft omega, is measurable regardless of this filtration. And for every t, ft, which is a random variable, right, is ft measurable.
And that property that I mentioned, is it the same as progressive measurable?
That means what you mean by f, like.
So we take f, and we consider it only on the interval 0t.
And what we do with
function,
omega?
I'm not sure, sorry.
So we consider like omega s to f s omega when s belongs to 0t and omega belongs to omega. Do you mean this?
Yeah, I think so.
This is exactly progressive measurability. Like just here. Here, we consider this on small s. For s this is less than t, the corresponding sigma algebra. The values live in Rd with Borel sigma algebra.
Thank you. I also wanted to say that the material is a bit too intense for me in terms of speed, so I can't always follow along. I don't know about the other students.
This is a good feedback. Valuable. Good. I think then we will try to proceed slow in a more restricted way next time.
Thank you.
But you're welcome but next time it will be easier, much easier.
Mhm.
Okay, are there any other questions? Good, then have a good day and we will see each other next time. And please contact me, new participants, please contact me so I can send you links.
Thank you.